Hello students, in this lecture we'll discuss how to find order of an element. Does the order of every element of a group exist? If the order of element exists in a group, then will the order of their product exist? If the product exists, will is the order of the product is the product of their order? Will uh, we'll discuss such problems in this lecture. For, the, for that, we just let us take first example, first question. Let G is a function of a function f set of all f such that f is a function of real f is set of all real valued functions which are one as well as all two. Let G this set of one two functions be a group under the operation of composition of functions. So, we need to be a group under the complete functions. Let f1 f2 belongs to G, means f1 f2 both are 1 as well as 2, and G is a group be two elements such that f1 of x is equal to minus x and f2 of x is equal to 1 minus x. Then prove that order of f1 is equal to 2 and order of f2 is 2, but order of f1 and f2 is not this. So in order to show order of f1, so f1 square of f is equal to f of f1 of f1 of x. F1 of x is equal to minus x. So this is equal to minus of minus 1 is equal to x. So f this means f1 square of x is equal to x implies uh, f1 is of order 2. Similarly, f f2 square of x is equal to f2 of f2 of x. So f2 of f2 is equal to f2 is 1 minus x, f2 of x is equal to 1 minus 1 minus x, this is equal to 1 minus x is equal to x. So cancel this with x, order of f2 is equal. But order of f1 to f2 is equal to f1 and f1 of f2 of x, f2 of x is 1 minus x, f1 of f2 of x is equal to minus of 1 minus x is equal to minus of 1 plus x. Then again, f1 of f2 of f1 of f2 of x is equal to minus 1 of minus 1 of x. Is minus 2 minus of x is equal to minus 2 of x. So this implies f1 of f2 of square of x is equal to minus 2 of x, minus 2 plus x. Therefore, f1 f2 of raised to n to find the composition n times f1 f2 of raised to n of x is equal to minus n plus x. Hence the order of this does not exist. And next is let let G is the set of second order matrices A, B, C, D, such A, B, C are real numbers, and A, D minus B, C not equal to 0 means this is set of second order non-zero matrices. Under the operation of multiplication of matrices, like this be a group under the operation of multiplication matrices, and let A is equal to this, be two elements, then prove that order of A and order of B is 2, but order of A into B does not exist. Now again, A square, or to find order of A square n must be equal to E. To find order of A into A, because this is identity matrix. A square is equal to I, this is order of A is equal to 2. Similarly, B square is equal to B to B, B to B is equal to I, this order B is equal to. If you find A into B is equal to, this is not equal to I. So A into B into A into B, this is equal to AB square comes out to be 1, 2, 0, 1. So if you multiply AB n times, you get 1 n 0 n for all n. So this implies order of the product AB as well. This order of A exists, but order of B exists, but order of A the product may or may not exist. Now let's say quaternion group. Quaternion group G consisting of plus minus I plus minus L plus minus M plus minus N elements. B the group be a group of quaternion under the multiplication. Then order of L, order of M is equal to 4, and order of N is equal to 4, but order of LM is not equal to order of L into M. So we have proved it earlier because L is equal to 4 is equal to M is equal to 4 is equal to 4 is equal to 1, LM is equal to N. So let us show it here also. L square is equal to this is L into L. L to L is minus 1, 0, 0, 1. Multiply them, row to column multiplication. Similarly, L square into L square, L whole square, L square, L square is equal to I. Order of L is equal to 4. Similarly, we can multiply M into M into M square into M square. Again comes out to identity. So order of L square, L is M, order of M is M, order of N is M. If you put an element, this comes out to N. So what order of N is 4? Order of N is 4. Order of L is equal to 4. Order of N 4 into 4 equal to 8. So order of N LM is not equal to order of LM comes out to be N. So order of N is 4. So the L order of L into L of order of L into order of M. Order of L into order of M. Order of L into order of M. This is equal to order of L into order of M. Order of M is equal to 8. Order of L into M is not equal to order of L into order of M. Now let's take a symmetry group. Symmetry group S3 of 3 elements. I is 1, I 1 2 1 3 2 3 1 2 3 1 3 2. B the symmetry group on 3 elements 1 2 3. Let A consists of 1 2 and B consists of 1 2 3. Then order of A into B is not equal to order of A into 1 2. But product is not equal to A is equal to 1 3 1 2 6. A is equal to 1 2 2 1 3 3. 1 2 3. B is equal to 1 2 2 3 3 1. Symbol position is. So A into A is equal to comes out to be into 1 2 2 1 1 1 2 into 1 1 2 2 2 3 3 3 equal to I. So A square is equal to I, the order of A is equal to 2. Similarly, B square is equal to B into B 1 2 2 3 1 3 1 2 2 3 1 3 2 3 3 1 2 1 3 1 1 2 3. So B square into B comes out to be B is equal to 1 2 3 use this and this will use this. In materialism, this comes out to be B cube comes out to be and B cube comes out to be I. So order of B. Order of B is equal to 3. So or AB is equal to equal to AB is equal to 1 2 3 and BA is equal to 2 3. So AB square is equal to AB into AB. So I order of AB is 2. Order of AB is 2. So order of A and order of B is 3 to 6, but order of AB is 2. So order of AB is not equal to. This is not only possible the order of AB. Then under what condition the order of AB will be equal to order of A? Now we'll prove a theorem based on this. At what condition order of AB comes out to be order of A into order of B? Now this theorem is if A and B are any two elements of G such that AB is equal to BA and order of A and order of B are relatively prime. Order of A and order of B are relatively prime, then prove that order of AB is equal to order of AB is equal to order of A into order. When will the order of the products their order? If the elements of the G commutes and their order are relatively prime. This is a condition that the order of product comes out the product of their order. Now, proof is let order of A is equal to M, order of B is equal to N, and their order are relatively prime. And let order of A be equal to A. Now, what to prove here is A is equal to M into N. Order of product is product of their order, where AB is equal to BA and their order of A and order of B are relatively prime. Now, first stage, let us take E to be equal to N is here, A B raised to power N here. In this we have proved the also this holds true in the group. So A B raised power n k is equal to A raised power n k, B raised power n k. Now again A raised power n k, B raised power n, B raised power n, order of B is n. So or B raised power n k, B for n, order B is n, or B raised power n is equal to E. E raised power k, this is equal to E raised power n k, E raised power k is equal to E. So E raised power n k, what order of A is m? So A raised power n k is equal to E, and order of A is n implies, and m and n are relative prime implies m must divide n k. M divide n k, but they are relative prime. So m and n are relative prime. M can't divide n. Therefore, m must divide k. Similarly, we'll take in the first step we take E is equal to AB is n k. Now we'll take E is equal to A raised power AB raised power m k. This is already laws of this holds true in a group. So AB raised power m k is equal to A raised power m k B square. A raised power m k can be written as A raised power m raised power k is equal to A raised power order of A is m. So A raised power m is E. E for k is equal to E. So this is equal to E into BMK is equal to BMK. Order of B is n. B raised power mk is equal to E, and order of B is n, implies n must divide mk, but m and n are relative prime. So that means relative prime means n can't divide m. So for this m to divide the product, n must divide k. First and second implies m divides k, n divides k. Therefore, LCM of m and n will divide k. M and n will divide. We know that if we have two positive integer, then LCM HCF of two numbers into LCM of two numbers is equal to their product. But HCF of two numbers are relative prime is equal to 1. Therefore the LCF number is 1. So substitute 1 here. So LCM of those numbers which are relative prime is equal to their product. So now M and LCM of LCM implies this implies the third and fourth implies m into n divides k. Again, AB raised power mn is equal to A raised power mn, B raised power mn, A raised power mn is equal to B to B, A raised power m raised power n is equal to B raised power n raised power m. So A raised power m, order of A is equal to m, is equal to E raised power m, order of A B raised power n, A B raised power n, order of B is n, so A B raised power n is equal to E raised power m, E raised power m is equal to E, E to m is equal to E. E to n is equal to E, is equal to E into E is equal to E. So AB raised to mn is equal to E implies, but order of AB is equal to K. This implies K divides mn. The first mn divides K, then we proved fifth and sixth we have proved m K divides mn. So fifth and sixth implies K is equal to mn, K is equal to mn, K is equal to mn. Equal to mn. That is order of AB is equal to order of A into order of B. Now important idempotent element. In a semi-group G, an element is said to be idempotent element if A scales to B. Now prove some result based on this. Show that if G is a group and A belongs to G is an idempotent element of G, if and only if A belongs to G is idempotent, if and only if A is equal to E and the identity element of G. Now solution is necessary part. G is a group. G group implies A belongs to G be the idempotent element of G. Necessary part here. Proving G is a semi group. Semi group. Okay, right? Semi group is closure and achievement holds true in it. G is a semi group. Okay, semi group. show that if G is a group and A comes to G is an idempotent, it contains A to B identity. Now this is the part G is a group and A comes to G is idempotent. That is, idempotent with A square group here. Now A square can be written as A square equals A to A is equal to A. A is written as A to E. Now then left cancel. G is a group, so both cancel are hold true in G. So apply left cancel by A inverse. G A if you G inverse belongs to G. Inverse this one goes to A is equal to E. So let substitute part that is equal to E, identity element of G. Now multiply this by now take A square is equal to A into A is equal to E, so A is equal to E, this is equal to E. Now again A is equal to E, so A square comes out to E, A square comes out to E, so A is equal to E, A is atom. Here is A square is equal to A into A is equal to E, given is there, substitute addition, so A into E, substitute A square is equal to E to equal to E, so E. Let G be a group such that A square is equal to E for all equal to G, then show that G is an E group. Solution is that is equal to G. Now A square is equal to E, therefore A is not equal to E, B is not equal to A, B is not equal to E. Given is A square is equal to E, B also belongs to G, B square is equal to E, and A square is equal to A into A is equal to E, B is equal to B to E. G is group, therefore cancellation of whole true. Apply left cancellation law. Because B inverse, E inverse and B inverse is first and second, we got A is equal to A inverse into A and derivative law. A inverse is E into A is equal to E. So A inverse into E is equal to inverse. E inverse implies B is equal to inverse. Also A belongs to G, therefore AB is equal to the whole true. Closest property A into B belongs to G. Order of A belongs to G, therefore order of AB is equal to 2. So AB square is equal to 2. So AB implies AB is equal to AB inverse. AB inverse is equal to, we have proved in the group that inverse of product in Mr. order. So AB inverse is equal to B inverse into B. Put the value of B inverse equal to B, A inverse equal to A. This implies Gj and B is equal to B. If in a group G, A raised to 5 is equal to E and A B inverse is equal to B inverse for all A belongs to G, then prove that if B is not equal to E, then order of B is equal to 31. Given G is a group, if the AB X belongs to G, therefore X inverse AX or this N is equal to X inverse is the N X or inverse or also. Now B square is equal to, given is B square is equal to A B inverse. First, squaring both sides is equal to, and using this theorem time and again, B square is equal to A B inverse square is equal to A B square inverse. Substitute B square here. Now A into A square, B inverse into B inverse square, B. Now again squaring this, so this is equal to, using the same theorem, B square is equal to A square, A is the minus 2 square, using the theorem is equal to A square, B square, A square inverse, A inverse square. Again place the substitute value of B here, A cube is equal to B, A is to minus 3. Again squaring, 16 is equal to A square 8, 16 is equal to A cube B A is minus 3 whole square is equal to, using the same theorem, A cube B square A is minus 3 square, substitute to B square here again, and again squaring we got B raised 32 is equal to A raised to 4 B square, substituting the B square here, this will be A B A inverse, this is a multiplying time, A is 5B inverse. A is of 5 is equal to E given, therefore A is to minus 5 is also E, it belongs to G group. We have put the same thing. This is equal to B is equal to B is equal to B into E, B inverse B is equal to B, applying right cancellation law. Therefore, B inverse into B into B is equal to E, into B is equal to E, the B is 31 is equal to E, implies order B. Find the order of each of the element of the group J consisting of 1, 2, 0, 1, 2, 3, 5 under addition model 6. इसलिए G with binding coefficient addition model 6 G group. G consists of 0, 1, 2, 3, 5. Under the composition addition model 6, here 0 is the identity element. We know the order of identity element is 1. So order of 0 is equal to 1. So order of 1. Similarly, we can find 2 into 1 is equal to 1 plus addition model 6 1 is equal to 2. Then we divide this 2 by 6, and this 2. Similarly, 3 into 1 is equal to 1 plus addition model 6 2 is equal to 3. 3 divided 6 is 3. Remainder is 3. 4 1 1 plus 3 addition 6 3 4 4 divided 6 is 4. Remainder is 4. 5 1 is equal to 1 plus additional 6 4 is equal to 5 5 is the remainder divided by 6 is 5 remainder and 1 into 6 into 1 is equal to 1 additional 6 5 is equal to 0 and the element so order of 1 is 6. Similarly, or 2 2 2 is equal to 2 additional 6 2 2 plus 4 divided by 6 is equal to 4 it is 4 or 3 into 2 is equal to 2 additional 6 4 4 plus 2 6 6 plus 6 0. So this is equal to 0 order of this is equal to is 3 or 3. Similarly, we can find the order of order 3 is equal to 2, order 4 is equal to 3, order 5 is equal to 6.